Let's talk about concrete. It's literally the foundation of our world, the single most used building material on the planet. But for all its incredible strength, it has this one hidden weakness, a problem that engineers have been wrestling with for decades. Well, today we're diving into a fascinating study that might have finally cracked the code, showing us how to build a better, stronger, and much longer-lasting beam.
So here's how we're going to break it all down. First, we'll get into the fundamental flaw in modern concrete, this big problem of rust and snap. Then, we'll reveal the super elegant hybrid solution that scientists came up with. We're going to see how they tested it, to destruction of course, and then use AI to perfect the design. And finally, we'll look at what this breakthrough really means for the future of our cities and our infrastructure.
All right, first up, let's talk about concrete's biggest vulnerability. See, concrete is amazing when you squeeze it. It has incredible compressive strength. But the moment you try to bend or stretch it, well, it's actually pretty weak. And that's exactly why we have to reinforce it.
So it's the real weak link here. It's not actually the concrete itself. Nope. The Achilles heel is the metal bars we have to put inside of it. And for engineers, the choice of what to use has always been this really tough compromise.
Okay, so you've basically got two options. On one hand, there's regular old steel rebar. It's strong and, this is key, it's ductile. It bends and stretches before it breaks, which gives you a clear warning sign that something's wrong. But, and it's a huge but, steel rusts. We all know this. Then on the other hand, you've got this stuff called Glass Fiber Reinforced Polymer, or GFRP. It's awesome, super strong, and completely rust-proof. The problem? It's brittle. It doesn't bend, it just snaps, with no warning at all.
So you see the dilemma, right? Engineers have been stuck. Do you pick the one that gives you a warning but will eventually corrode away, or do you pick the one that lasts forever but could fail suddenly and catastrophically? The real challenge, the holy grail, is to get all three things at once: strength, rust-proof durability, and that safe bending before breaking failure.
And that leads us right to the brilliant idea at the heart of this research. Instead of trying to invent some new, miracle material from scratch, these engineers asked a different question. What if we just combine the two we already have, but in a really smart way?
Now, before we go any further, let's just lock in that key term, ductility. It sounds technical, I know, but it's actually super simple. Just think about a paper clip. When you bend it, it doesn't just snap in half, right? It bends, it stretches, it deforms. It gives you plenty of warning that it's about to fail. Well, in a bridge or a building, that warning is everything. It's the difference between a safe repair and a sudden disaster.
So, the solution they came up with is just so elegant. They created a hybrid beam. Here's the concept. You strategically place steel bars right in the middle to act as that ductile safety net. They're designed to be the first to bend, to give you that critical warning if the beam is overloaded. Then, you surround that steel core with the high-strength, rust-proof GFRP bars. They provide most of the strength and act like a shield, protecting the entire thing from corrosion. Best of both worlds.
You know, the whole idea behind this was captured perfectly in an earlier study, which said, the yielding of steel enables ductile failure with sufficient pre-failure warning. That one sentence is the whole ballgame. It's all about using each material for what it's best at, so you get the safety of steel and the longevity of GFRP all in one package.
Of course, an idea sounding brilliant on paper is one thing. You've got to prove it works in the real world. So the researchers went to the lab to see if this hybrid beam could actually handle the pressure. It was time to put it through the gauntlet.
And they didn't mess around. They built 13 different concrete beams, some with just steel, some with just GFRP, and a whole bunch of different hybrid combinations. And then they did what engineers do best. They systematically bent every single one of them until they completely failed.
And the results? They were honestly remarkable. What they found was that in many cases, swapping out some of the steel for GFRP didn't just maintain the beam's strength, it actually increased it. In one test, get this, replacing half the steel with GFRP actually made the beam over 10% stronger. This wasn't a compromise at all, it was a straight-up upgrade.
And this right here shows the second huge finding. The hybrid design completely solved that scary brittleness problem. That steel core did its job perfectly. It made sure that even as the beam got close to its breaking point, it bent significantly, providing that crucial warning before anything catastrophic happened. They'd done it. They hit the engineering trifecta: strong, durable, and safe.
Okay, so the lab results were a huge win. But here's the thing, physically building and breaking beams is slow and it's really expensive. To truly unlock this design's potential and figure out the perfect recipe for any situation, the researchers needed to go digital.
so they turned to AI to build a virtual testing lab.
They took all the data from their 13 beam tests and then combined it with data from hundreds of previous studies. This created a massive data set of 212 unique beam experiments. They poured all of this information into a machine learning model to see if it could actually learn the complex physics of how these things work.
The specific AI they used is called XGBoost, and you can think of it like an incredibly smart student. It builds one model to make a prediction, then it looks at where it messed up, and then it builds a brand new model specifically designed to fix those mistakes. It just keeps doing this over and over, getting smarter and more accurate with every single step.
So how good was it? Incredibly good. On data it had never seen before, the XGBoost model could predict a beam's ultimate strength with 95% accuracy. The AI hadn't just memorized the data, it actually seemed to understand the underlying principles well enough to make really solid predictions.
Okay, but this is where it gets really exciting. Because having an AI that can predict what will happen is one thing, but being able to ask that AI why it's making those predictions, that's the next level. It was time to unlock the AI's secrets.
This has always been the big challenge with complex AI, right? We call it the black box problem. You put your data in, you get a really accurate answer out, but you have no idea how it came up with that answer. So, how do you peek inside?
Well, the answer is a pretty cutting-edge technique called SHAP analysis. It's part of this growing field called explainable AI, and it's basically like a translator for the AI's brain. It lets us see exactly which design choices, like how much steel you use or how wide the beam is, had the biggest impact on the final outcome.
And what the AI told them was surprisingly clear. It revealed that the single most important factor for making a beam strong is the amount of steel you use. After that came the beam's width, and then the amount of GFRP. For the very first time, engineers have a precise, data-driven recipe to cook up the perfect hybrid beam for any job.
So, let's bring this all home. We've got a clever new beam design, we've proven it works in the lab, and we've optimized it with AI. But what does this actually mean for the world around us? Why should you care?
Well, first, it means we can build things, bridges, buildings, seawalls, that last for generations, resisting the rust that eats away at our current infrastructure. Second, we can make those structures fundamentally safer, with that warning system literally built right in. Third, we can design things more efficiently, using AI to get the absolute most performance out of every bit of material. And finally, this whole approach is a blueprint for innovation, proving that sometimes the smartest solutions come from combining the best of what we already have.
This research doesn't just give us a better beam, it gives us a whole new way of thinking, and it leaves us with this really fascinating question to think about. If we can solve the ancient problem of rust and brittleness just by combining steel and glass fiber, what's the next hybrid hero out there that's waiting to change the way we build our world?